Welcome back everyone. In this lecture I am going to complete the proof of Mackey's irreducibility criterion. So, for that let us recall the Mackey's theorem that we proved in the last class. So, we wanted to actually compute the restriction applied on the induction and how it behaves in terms of the subgroups. Okay, let me just recall the statement. So, as before, let us fix this H and K to be subgroups of G, and then this S to be the set of representatives of this double cosets H mod G K. So, then we proved that for any function f, class function f from z of C k. So, this is given this function. So, what we can do, we apply the restriction from G to H and then the induction from K to G and then apply it on f. So, this is going to be written very explicitly in terms of this other induction applied to the restriction. So, sum it over S in S such that induction from H intersection S k S inverse to H and the restriction from S k S inverse to H intersection S k S inverse, and you apply this on F s. So, where this F s is a class function from this subgroup C S k S inverse, that is given by F s of x equal to f of S inverse x s. This is given by the conjugation. So, this is what we proved in the last class. So, let us actually use this result in order to conclude the Mackey's irreducibility criterion. So, for that we are going to only fix H to be a subgroup and then we take K to be H and then apply this theorem. Okay, so, here is the theorem. So, we take H to be a subgroup of G. So, then we want to actually understand the induction of any representation of H. So, let us fix phi to be a representation of H. So, let us say the degree of this representation is D. So, this is a representation of H. So, then we want to look at the induction of this phi from H to G, and we want to understand when it is irreducible, and we prove that it is irreducible if and only if the following conditions actually satisfied. The very first condition, this phi must be irreducible. So, that is the first condition. The second condition, so the representation that we see, the restriction of H to H intersection S H S inverse of phi and phi s. So, we demand that they are indeed disjoint representations for all S not coming from H. So, the representations restriction of phi from H to H intersection S H S inverse and the restriction of phi s again from S H S inverse to H intersection S H S inverse. So, these representations we demand to be disjoint, and this is true for all S not coming from capital H. Note that phi s is nothing but just phi of S inverse x s. Okay. So, let me recall phi s of x is given by just phi of S inverse x s for all x in SH S inverse. So, this is the twist of the original representation phi by this conjugation given by S, okay, and this is again representation that is easy to verify. So, now this Mackey's criterion very explicitly states when this induction is irreducible in terms of these two conditions. So, let us see let us see how one can prove this using the previous result. So, we denote this chi to be the character of this phi. So, it is character of H, and as before let us take S to be the set of complete set of double coset representatives. So, this is a complete set of double coset representatives of this double cosets H mod G mod H. So, now we will assume that without loss of generality that 1 is in S. So, we just assume this without loss of generality, because this 1 will corresponds to the double coset H 1 H, which is H. Okay. H is going to be double coset with respect to the groups H H. So, that is obvious to see. So, now if S is indeed 1, so then what happens to H intersection S H S inverse, which is exactly equal to H intersection H, which is exactly H. So, now denote this S hashtag to be all the elements which are not 1 from S. So, now let us rewrite the restriction applied on the induction of chi. So, using the earlier observation. So, if you compute this character, so where you take chi, you induct from H to G and then restrict G to H. So, this is going to be given by chi plus summation S in S hashtag, and you take again like this chi S, apply the restriction and then induction. So, the restriction is from S H S inverse to H intersection S H S inverse, and induction again from H intersection S H S inverse to H. So, this is what we get. So, when S is equal to 1, you can see that this term indeed get collapsed. Okay. When S equal to 1, so then this H intersection S K S inverse becomes H, and everything is like induction restriction you are doing from H to H, and induction you are going from H to H. So, you are not really doing anything. So, the character stays as it is, even the twist is trivial twist. So, the character stays as it is. So, that is how you are getting chi here. So, this is the formula that we proved before. So, now we just use Frobenius reciprocity twice and then use this formula to compute the following. So, you compute this inner product of the induction from H to G of this chi. So, which is given by, you can take this restriction from H to G applied on the induction H to G chi. So, this is the Frobenius reciprocity. Now, we can replace this by this. So, then what we get? We get exactly equal to chi inner product with chi plus summation S is running over in S hashtag, where you have this induction H intersection S H SH S inverse to H applied on the restriction on chi S comma chi, where restriction is again obtained from SH S inverse to H intersection SH S inverse. So, this is what you are getting. So, now again what we can do, we can use Frobenius reciprocity, then this can be rewritten as follows. So, if you again use Frobenius reciprocity and rewrite, this is going to be chi comma chi, the inner product where summation S running over S hashtag, where you have now you keep this restriction chi S, and then this induction will be shifted to here as restriction. So, here let us keep this SH S inverse H intersection SH S inverse, but here this becomes a restriction from H to H intersection SH S inverse applied on chi. So, this is what we get. Now, note that this is chi is character of representation of H. So, that means this is indeed greater than or equal to 1. So, now here we have two different characters. One is the restriction of chi from H to H intersection SH S inverse, and the restriction of chi S from SH S inverse to H intersection SH S inverse. So, it is like xi 1 and xi 2. So, these two characters are there, and the inner product of that, for sure we know that it is non-negative. Okay, that is all we needed. So, the inner product of this is given by this sum of these non-negative terms, where the first term we know for sure it is greater than or equal to 1. So, now if we use this criterion of irreducible characters, so we know that the induction from H to G of chi, so this is irreducible if and only if the inner product of this induction is supposed to be 1. So, that means if and only if you can see that this term must be equal to 1 and this term must be equal to 0. So, then we can write down that as chi comma chi supposed to be 1 and this restriction of chi S and the restriction of chi. So, these inner products supposed to be 0, but what is the meaning of that? That means they are disjoint. And this is true for all S in, not in S hashtag. Now, note that this capital S is actually chosen to be some complete set of double coset representatives of these double cosets H mod G mod H. So, that means we can very well actually replace this S hashtag by any element that are not in H, okay, because if S is not in H, so then it is not difficult to actually come up with some S dash, which is the complete set of double coset representatives of H mod G mod H, such that this S is an element of this S dash. So, this is possible, okay. Maybe you can take it as exercise. So, what is the exercise? The exercise is that given S in S dash, there exists S dash which is a complete set of double coset representatives of this H mod G mod H, such that this S is going to be element of S dash, and this is true. Since this is true, So, you can actually replace this S hashtag by any S not in H, that is not a problem. Okay. So, basically we proved that this induction is indeed irreducible if and only if this chi inner product must be 1, that means it is irreducible, and these representations, they are supposed to be disjoint for all S not in capital H, and this is what we wanted to actually prove, and that gives the characterization. So, let me just write it down. So, this induction from H to G of phi, so this is irreducible if and only if phi is irreducible. So, that is the first thing, that means the inner product of chi is 1. The second thing is, look at these representations, restriction of phi from H to H intersection SH S inverse, and the restriction of phi S, which is the representation that is obtained by twisting the action of phi via the conjugation by S. So, then this representation restricted to SH S inverse to H intersection SH S inverse, and we demand that they are disjoint. So, that is the meaning of saying that the inner product is 0, this inner product is 0, and that is indeed we demand to happen for all S in capital H. But in practice we can choose one set of double coset representatives, and then we can simply verify that these are indeed disjoint. So, that is much more easier than like proving it for all S not in capital H. So, this actually kind of completes the proof of Mackey's irreducibility criterion. So, indeed like we said in the beginning, if you assume that H is normal subgroup, so then things actually looks much more simpler, because once H is actually normal subgroup, then these double cosets are same as left cosets or the right cosets, and in particularly SH S inverse is going to be H for all S in G. So, in particularly what we have is H intersection SH S inverse is going to be H. So, that means you can see that these restrictions are somewhat easier to understand, okay, in this case. So, what happens in this case? All you have is this restriction is H intersection SH S inverse becomes H. So, basically the restriction of H H to H intersection SH S inverse phi is exactly the restriction of H to H phi. So, it is exactly phi. Similarly, the restriction of SH S inverse, which is H to H intersection SH S inverse phi S, is going to be exactly phi S. So, now we can simply rewrite in this case when H is normal in G. So, then this induction of chi from H to G is irreducible, or the representation phi if and only if phi is irreducible, that is important. The second thing is these representations phi and phi s, which are obtained by twisted. So, this phi s, that is not supposed to have phi as an irreducible constraint. So, phi and phi s are supposed to be disjoint. for all s not in H, but this also one can replace as, because already we know that phi is irreducible. So, phi does not appear in phi s. So, we can replace as this. Okay. So, when H is normal, then these two conditions, phi is being irreducible and phi and phi s are being disjoint, or phi does not appear in phi s, that actually characterize this induction being irreducible. Okay. So, this actually complete the proof of Mackey's irreducibility criterion. So, this is actually the important result that I wanted to cover in this section. So, maybe with this I will stop here, and then we can start with some Fourier analysis on finite groups in the next class. Okay, thanks. I will stop here.